This is d dimension, right? There are d numbers. Now I have to go down, right? So what should I do?
Px.
Yeah, px, right? Px will give me lower dimension. So if x is d cross 1, this should be some k cross 1, say k cross d, right? So it will be k cross 1. So k is much smaller than d. Okay, fine. So now what is the problem that you will solve? So you know how to bring everything down, right? But how do you ensure? What is the problem now? See, one thing that I have to ensure is if you look at 2 points in different classes here, when you project it, the distance should be maintained, right? It should be as large as possible, right? Do you agree? And within the cluster, right? If you take these points within the cluster, it should maintain distance, right? That's what you want to do, right? So how do you pose that as a problem? What do you think? What do you think if I want to solve this problem? What kind of problem should I write so that I can hope to solve in this course? What is it that I have to do? What is it that I have to do? See, first of all, I look at two things, right? So P xi, this is the ith data point, P xj. Now, suppose I and j belong to the same cluster. For example, both are spans. What is it that you expect? What should be Pxi and Pxj? These two are vectors in lower dimension, right? It should be
Close to each other.
close to each other, right? If they are from different, it will be far off, right? So essentially, how do you measure closeness? To 2 now. Maybe I'll take square also, right? Square is easy to handle, right? Okay, now this is among two nodes, two data points, xi, xj. Now, if you look at, for example, the distance across, right? I should ensure that they are far off, but within they should be close, right? So what should I do? I should sum over all I. You fix a j, okay? J in some cluster, and I is in some other cluster. So if you fix j, I should sum over all possible i's in the other cluster. So let me call this as cluster 1. Okay, cluster 1 is, for example, 1, 2, 3, 4 till 10, and I should sum it over all j cluster 2, right? It will give me the sum of the distances across all possible points, across the two clusters, right? Do you agree? Right? In practice, people won't do this, but this is one way of posing the problem. Now, I want to ensure that this is as large as possible, right? So I have to figure out a matrix P such that it's as large as possible, right? Separation. But what should I do? Of course, I can always do by, I don't know, many things, right? So what should happen to the inter within the cluster? It should be small, right? How do I write that? So again, you look at, I'll write a different one. I'll say PK and maybe I'll use LM. Okay, PL, PXL, PXM. This distance should be as small as possible, right? I'll say less than some delta. This should be true for all to C1, right? And for all LM belonging to C2. Okay. That means L and M you pick from one cluster, it should be very close to each other. If you pick LM to the other cluster, it should be close to each other, but across it should be as far as possible, right? This is how you come up with a problem. Then you stare at it and say we can simplify and do something else, or maybe you can come up with an algorithm which is heuristics and see what is the performance of this. So many things can be done, right? A good problem is half the solution, right? So you should come up with a good problem first. Okay, is this fine? Okay. And of course, you can pose several other. So let me look at one more, which will sort of motivate few things. So suppose I give you this is like a linear separation problem. So so suppose I give you two data sets, okay, something like this. Right? How do you separate? Well, straight line, right? Of course, you can also use curved lines, but straight line is the most obvious, right? In n dimension, it's a hyperplane, right? That's how you separate out, right? Now, what are the questions that we can ask? Suppose I throw data like this at you, let's say 10,000 dimensional data points. You cannot plot and see whether you can separate, right? So what is it that you have to do? You have to mathematically verify whether it is separable by a hyperplane, right? So the first question that we can ask is, are the data points separable by a hyperplane? We will see what a hyperplane is. What is the next question? If so, the answer to the first question is yes. Then how do you find that hyperplane, right? If so, how do you find the hyperplane? Well, I think in the first class itself, I came up with a problem which is straightforward, intuitive, but that's not how you solve this problem, or that's not how you pose the problem. Also, it's very. I looked at indicator function as losses, and then we pose this problem as a minimization of losses with respect to the parameters of your hyperplane, right? Find the hyperplane. So in both the cases, you came across this word hyperplane. Let's try to understand what a hyperplane is, because this will be very, very important throughout. If you look at any optimization, hyperplane plays a very, very important role, even in duality theory. So let's take this opportunity to understand what a hyperplane is. Well, hyperplane is a plane in higher dimension. That's all. So what is a plane in higher dimension? How do you describe a plane? Suppose I give you this. It's a plane, right? So how do you describe this plane? Of course, let's say everlasting. It's not, although I have written a box here, it extends to infinity. So how do you write a hyperplane, or mathematically describe a hyperplane, given that you have learnt linear algebra? What are the two ingredients? So if I have to, suppose, let's say there is a contest wherein I have to give little information, but you should be able to write the hyperplane that I want to write. So what is that little information that I should give you? First thing is the point, right? So at least I need one point through which the hyperplane passes, right? For example, a line, if I want to describe line, Euclidean geometry, right? Euclid wrote that 2000 years ago. You need 2 points, right? That's all. But in general, if you look at hyperplane, 2 points are not enough, right? I can have infinitely many planes passing through the 2 points. So what else you need? Let me call this point as some, I don't know. Okay, let me rename it. Let me name it later. Okay, maybe you. Okay. What else you need? You need a perpendicular to the plane, right? At this point. Let me call this perpendicular P. Okay. Well, the perpendicular is well, this P is not from, this is not P. Okay, so this is like the vector joining U and this point is, or the direction in the perpendicular direction at U is called P. Okay, so P is, let's say, a unit vector. Okay, so let me also write that. Again, sake of simplicity, P need not be a unit vector. Okay, now is this enough to describe every point? Now, how do you describe a point, for example, here? Okay, this is a point X. How do you describe this point? You join a line, right? And this is orthogonal, right? Do you agree? Now we can use them. usual math. What is the usual math?